Hello and welcome to the second video of a series I will release alongside EvoLife version 0.6. In this video, we will explore the world objects and cell internals in detail. Let's start with the materials in the game world. There are 4 types of materials outside living cells. The first one, the most basic, is rocks. These do not have any special behavior, except that rocks can be static, non-moving objects. These are added at the start of the simulation at world generation. The user can add moving and non-moving rocks at the simulation anytime. The second type of object is gas bubbles, inspired by deep-sea gas vents. These vents are theorized to be the point where life began. In the simulation, gas bubbles are spawned by fields. These bubbles contain energy inside, which can be used by living cells. The amount of energy stored is set by the spawning field. The third type of object is dead cells. These are once living cells that died for one reason or another. These also contain energy inside, decided by the circumstances of cell death. The fourth type of object is biomaterials. There are 26 of them, numbered from 0 to 25. These materials are produced and can be broken down by living cells. Each type has an energy value associated with it, set during world generation at the start of the simulation. Materials can interact in a variety of ways. Living cells can stick to objects, produce biomaterials, or can break down world objects that contain energy inside. They can also siphon out energy directly from living or dead cells. These interactions are decided by the DNA of the cell. Each interaction requires an organelle to perform. Biomaterials can stick to all object types. The decision of which biomaterial interacts with which objects happens at the start of the simulation during world generation. This way, every biomaterial has a consistent behavior in each world. Let's deep dive cell internal workings next. Each cell keeps track of its own internal status, like its age, its energy usable for actions, and hit points. Each cell has 16 behavior slots to grow organelles and behavior logic, customizing how it behaves in the world. When a cell is born, it receives a random amount of cooldown up to 9 game ticks, during which DNA execution is temporarily paused. A game tick is one step forward in the simulation. On 1x speed, each frame 1 game tick occurs. On 2x speed, 2 game ticks occurs between frames. Each cell belongs to a species. The species definition sets multiple properties of the cell. In the real world, cells have surface proteins to identify each other. In this simulation, this is represented by a 15-bit number. Touching cells can behave differently depending on how much their 2 surface protein numbers match or differ. The starting color of the cell is also coming from the species definition, as is the DNA sequence, which is executed by each cell as a program of life. The sequence consists of 1 or more DNA pieces. There are different DNA pieces for different tasks. More on that later. How does a behavior slot look like? As mentioned before, there are 16 of them per cell. Each behavior slot has an opcode defining what is happening in that slot. In a fresh cell, nothing is happening. To update the opcode, the cell has to execute a DNA piece that describes what operation will take place in that slot. This can be an organelle, for example a flagellum, which propels the cell forward, or a sense organelle to detect the surrounding of the cell. It can also be glue logic to connect up organelles or provide periodicity. Each behavior slot can have multiple inputs and one output. Each organelle will gather its inputs and update its outputs each game tick. The default value of the outputs are coming from the species definition. Each output register has two parts, validity and data. Validity is defined as a single bit. The data in the registers can be valid or invalid. The data part is represented in 8 bits. It can be interpreted as a scalar value, defining a simple number between 0 and 2055, or it can be interpreted as direction. 0 means right, 64 is up, 128 is left, and 192 is down. Cells can heal themselves under the right conditions. Every 100 game tick, if the cell has more than half of its energy, and it is more than 1000, if the cell is missing hit points, it will regain one, costing 500 energy. Cells can die in 4 ways. The first is if the cell becomes too old. The second is running out of energy. The third is running out of hit points. The fourth way is special, as it is initiated by the cell by executing a special DNA instruction. After death, the cell becomes a dead cell particle, where the energy stored will be the remaining energy of the cell and its remaining hit points multiplied by 2050. All connections initiated by the cells disconnect. An overview of what happens with a single cell during a game tick. First, it heals if the game tick has the right timing and conditions allow. Then it executes the current DNA piece. Executing a DNA piece takes more than one game tick, so it might not finish with the current one. Then, whether it is finished executing the current DNA piece or not, it executes all behavior slots. Register reads collected as inputs are always the value of output registers from the previous game tick. Each slot executes and writes its new output. After this happened, the cell checks its properties and dies if it is out of luck. Let's talk about DNA pieces next. There are 9 different types of DNA pieces in this release. Each one achieves different things. Let's go one by one. The first one is NOP. It takes 50 game ticks to execute, and it uses 1 energy per game tick. It does nothing. The second one is Math. This DNA piece is a behavior slot opcode. After executing it as a DNA, it will occupy a behavior slot and will produce a new output register value every game tick. It takes 50 game ticks and 2 energy per ticks to execute as DNA, except if the slot already contains the exact same opcode. Then it takes just 20 game ticks and 1 energy per game tick. In the behavior slot, it requires no energy to use. The operation defines what math operation will it perform as an organelle. The input and output of this part is the data part of the registers. It can add, multiply, calculate minimum, average, and more. The result passes through post-processing. In wrap mode, the result is divided by 256 and the remainder is taken as the final result. In clamp mode, results under 0 will be 0 and above 255 will be 255. Now that we know what happens to the data, let's see what we can do with the valid bits. Validity mode defines how the opcode handles the validity of inputs. Valid mode calculates and updates output validity each game tick. This can be valid or invalid. The behavior slot can have an invalid output this way. In enable mode, if the output would be invalid, it is not refreshed. Only valid values are written in the output register. Validity type defines how the output register valid bit is calculated. If the truth table is selected, the user can set output validity for the 4 combinations of the 2 input valid bit values. If compare mode is selected, the output bit will be calculated from the two input data values, ignoring the input valid bits. The first input always comes from a register. The second can come from a register or can be a constant value. The next type of DNA piece is sequence. This is also a behavior slot opcode with the same time and energy requirements as math. This opcode implements 11 types of higher level logic and sequences. The first higher level logic is priority list. This takes 5 inputs and the output will be the highest priority that is valid. The second is constant. This outputs a constant value with settable valid bit. The next one is attribute. It takes the energy or hit points of the cell, then outputs it after scaling. Rand is outputting a random value in the given interval every time there is a valid input. Beat is the first sequence. It has an internal counter that increases by 1 every game tick. If the internal counter reaches maximum, it outputs a valid 255. Otherwise, it outputs an invalid 0. Hold outputs the input value, but it holds the last valid value for the specified time after the input becomes invalid. Delay copies the input as well, but the output here stays invalid for the specified time after it becomes a valid input. Sine outputs a periodic sine wave. Phase step and time step together sets the frequency and jaggedness of the output. Valid input sets the phase of the sine wave. Square outputs a square wave. Duty cycle is settable, time step sets the frequency. Valid input sets the phase here too. Triangle and sawtooth outputs its respective wave as output. Value step sets the slope of the function, and the time step sets the frequency. A valid input here sets the output directly. The next type of DNA piece is organelle. This is also a behavior slot opcode with the same time and energy cost as math and sequence. Additional time and energy may be necessary. Each organelle adds its cost to the execution cost. Each organelle can add to the DNA execution time and energy cost and set energy usage in a behavior slot. There are more than 65,000 organelles in each simulation, each with its costs and parameters. An organelle can take inputs, like in which direction to swim for a flagellate organelle, and can provide outputs, like the direction of the detected touch from a sensing organelle. More on the organelles later. The first DNA piece that creates another cell is egg. It takes 50 game ticks and 2 energy per game tick to execute. The division happens directionally. It can be absolute or can come from a behavior slot output register. The cell can use an existing connection organelle to connect to a new cell. The DNA piece also provides an address from where the new cell will start executing DNA code. This method of cell division creates a fresh cell. Mutation happens during this type of division. More on that later. The fresh cell has an age of 0 and all of its behavior slots are empty. The energy and hit points of the original cell will be divided between the fresh and the original cell. So if the original cell has only 1 energy or 1 hit point when the division should happen, at the end of the DNA piece execution, nothing will happen. The new cell gets half of the original cell's hit points or 10 hit points, which one is less. It will get half of the original cell's energy or 5000 energy, which one is less. The original cell will lose the hit points and energy the new cell starts with. The second DNA piece that creates another cell is fission. It has the same time and energy requirements as the egg DNA piece. The direction of the new cell connecting to a new cell and the address is similar to the egg DNA piece as well. However, this method of cell division does not create a new cell, but a copy of the original. The age of the new cell and all behavior slots will be a copy of the original. One difference is connection organelles copy over, but their connections do not. Connection organelles are unconnected in the new copy. Hit points and energy are split between the original cell and the copy. If either one is 1, then the fission does not happen. The next DNA piece is jump. It takes 50 game ticks and 2 energy per game tick to execute. By default, the DNA sequence is executed sequentially and cyclically. However, after executing this, the DNA piece located at the selected address will be executed next. The jump can be conditional. If it is, then the jump will only happen if the selected behavior slot output register valid bit is matching the value that is defined in the DNA piece. The next DNA piece is AND. It takes 50 game ticks and 2 energy to execute. It codes for programmed cell death. After it executes, the cell becomes dead. The last DNA piece is wait. It takes 1 energy per game tick to execute. It can wait for a specified amount of time and/or it can wait for a behavior slot output register valid bit to have a defined value. Let's talk about organelles next. There are more than 65,000 organelles defined for each simulated world. Each has its own ID, type and type parameters. Some common type parameters are whole numbers up to 255 and signed and unsigned version of a fixed point number type where the increment between positive values is 0.05. Each organelle has its own time to develop, energy to develop, and energy to use value, which adds to the organelle DNA piece execution time and energy and sets the energy used when it is in a behavior slot as discussed before. Each organelle type subtracts its cost to use at different events. For each organelle type, we will discuss what it does in a behavior slot, what are its settable parameters, what it takes as input, when it is using energy, and what output it produces. The first type of organelle is spikes. When a cell grows spikes, it damages all touching cells. It has a settable attack parameter which describes the amount of damage the spike will cause. It takes no inputs, uses no energy, and does not change the output register of the slot it is in. The second type of organelle is cell size. This organelle changes the size and mass of the cell, modifying the maximum energy and hit points. It takes no inputs, uses no energy, and does not change the output register. The next type of organelle is cell wall. The cell strengthens, thickens its cell wall, reducing incoming damage from spikes and other effects. The organelle takes no inputs, uses no energy, and does not change the output register of the slot it is in. The next type of organelle modifies the color of the cell to the RGB value defined in the parameters. The organelle takes no inputs, uses no energy, and does not change the output register of the slot it is in. The next organelle type is active spikes. These behave like normal spikes, poking everything, but can be retracted. If the input it takes is valid, the spikes will be active. If the input is invalid, the spikes will be inactive. The organelle uses energy when it switches from active and inactive states. The output register of the organelle will be valid 255 if the spikes are engaged and invalid 0 if disengaged. The next organelle type is flex. This organelle dynamically modifies the size of the cell while keeping the same mass. Its parameter is the maximum change of radius. If the input is valid, the organelle uses energy and modifies the size of the cell. If the input is valid 0, then the change will be 0. If the input is valid 255, the change will be the maximum change. The output of the organelle is the last valid input it received. The next organelle type is heal, which provides additional healing on top of the one automatically happening every 100 game ticks. It has a cooldown parameter that describes how many game ticks it takes between heals. Internally, the organelle counts down, and when it reaches 0, it is ready for a heal event. It will heal if the hit points of the cell is less than maximum. The cooldown generates in a way that the product of the cooldown and energy used per game tick will be greater than 500. The input of the organelle enables the counter and healing. Energy is used if the cooldown counter is not 0 and the organelle is enabled. Output is valid 255 if a heal event happens and invalid 0 otherwise. The next organelle is flagellum. It is a long whip-like structure that helps the cell move. The parameter is the maximum force that is available. The organelle has two inputs, a direction and a force. The direction input decides in which direction the cell will move. The force input decides how hard the flagellum propels the cell forward. A valid 255 force input will use the maximum defined in the parameter, and the valid 0 will not propel the cell forward whatsoever. A flagellum organelle needs a valid direction and a valid force input at the same time to change direction and force. If the input force is 0 or the energy to use is 0, then the energy used will be 0. Otherwise, it is scaling with the input force, but at least 1. The organelle remembers the last valid direction and force input and does not change course until a new valid input pair is received. The output register of the organelle is the direction the flagellum is heading currently. The next type of organelle is produce smell. It has two parameters. The first is the smell ID, which identifies which of the 8 possible smells will be emitted. The second parameter describes the maximum amount that will be produced. The organelle takes one input, which scales how much smell is produced. If the input is 0 or the energy to use is 0, then the energy used will be 0. Otherwise, it is scaling with the input, but at least 1. The output will be the amount of smell emitted. The next type of organelle is produce biomaterial. It has two parameters. The first is the biomaterial ID, which identifies which of the 26 biomaterials will be produced. The second parameter is the cooldown, which describes how frequently the organelle can produce a biomaterial particle. Organelles generated with word generation have a cooldown, so the product of the cooldown and the energy used per game tick is more than the energy contained in the biomaterial. The organelle internally counts down, and when it reaches 0, it is ready to emit a biomaterial particle. The input of the organelle describes which direction the biomaterial will be emitted. If the cooldown is not 0, nothing happens. If the cooldown is 0, then a biomaterial particle is emitted and the cooldown resets. Energy is used when cooldown is not 0. Output of the organelle is valid 255 if ready to emit, invalid 0 if not. The next type of organelle is breakdown. The first parameter of the organelle is the type of material that the organelle breaks down. The second parameter is a cooldown. The organelle internally counts down, and when it reaches 0, it is ready to break down a material defined in the first parameter. Breakdown happens when the countdown is 0, the cell collides with the correct type of material particle, and the cell has capacity to store at least 100 energy. Each material that can be broken down stores energy inside. During breakdown, 100 energy is taken from the particle and added to the energy of the cell. If the particle has less than 100, then all remaining. If the broken down particle stores no energy after the transfer, the particle despawns. The cooldown resets after breakdown. The input of the organelle defines if the cooldown is happening or not. If the cooldown is already zero, breaking down a particle happens even if the input is invalid. Energy is used by the organelle when the cooldown is not zero and the organelle is enabled by a valid input. The output of the organelle is valid 255 if the cooldown is zero, the organelle is ready to break down, and invalid zero otherwise. The next type of organelle is siphon. It siphons up to 50 energy out of a dead or alive cell when colliding and receives up to 25 of it if the cell can store additional 25 energy. The defense level, modified by the cell wall organelle, reduces the amount of energy siphoned. The first parameter is the surface protein threshold. If more bits match between the surface protein numbers of the two alive cells, no siphoning will take place. This does not affect dead cells, no surface protein matching happens there. The second parameter is cooldown. This organelle counts down too and is able to siphon if cooldown reaches zero. The cooldown resets after siphoning happened. The input of the organelle defines if the cooldown is happening or not. If the cooldown is already zero, siphoning happens even if the input is invalid. Energy is used by the organelle when cooldown is not zero and the organelle is enabled by a valid input. The output of the organelle is valid 255 if the cooldown is zero, the organelle is ready to siphon, and invalid zero otherwise. The next type of organelle is sense direction, the first sense type. It has one parameter, whether it is sensing the fluid movement direction surrounding the cell or the cell itself. The input enables or disables sensing. It takes energy when the organelle is enabled. Its output is a valid direction when enabled and invalid zero else. The next type of organelle is sense smell. It takes three parameters, a smell ID, which describes which out of the 8 possible smells this organelle will sense, and two scaling factors. The input enables or disables sensing. It takes energy when the organelle is enabled. Its output is a valid scaled smell value when enabled and an invalid zero else. The next type of organelle is sense touch. It can be enabled and takes energy when enabled. Its output is the direction of the last touching object if enabled and invalid zero else. The next is sense damage. It behaves like sense touch, except it outputs the direction of the last spike poke or siphon that happened. The next type of organelle is sense color. It casts a ray from the center of the cell and reports the color of the first object in line of sight. It has two parameters. First is the length of the ray. The second is which color component will be the output. It can be red, green, blue, or gray. Gray is not real gray, but the average of the three color components. The organelle takes one input, a direction, where the ray will be cast. The organelle uses energy if it receives a valid direction input. The output is the color component the ray detected, or invalid zero if nothing is detected or the organelle is not enabled. The last type of sense organelle is sense cells. This organelle senses the number of living cells in a radius of the cell. It takes one parameter, the range of the sensing. The detection range will be around 5 times the range provided here. It takes an input which enables the organelle. It costs energy when enabled. Its output is a valid number of cells, including the cell using this organelle, if the organelle is enabled, and an invalid zero else. The next organelle types are connection organelles. They all share some common parameters. One is how long the connection will be. Another one is how strong it will be, how much stress it can tolerate. The next one is the type of joint. Rod joints resist pulling and pushing, and colored white in the middle. Rope joints resist only pulling, and colored gray in the middle. The next parameter is a list of what the connection will connect to. It can be rocks, other cells, and 26 types of biomaterials. When connecting to another cell, surface proteins play a role. Connections will only happen if the two cells have at least as many matching surface protein bits as defined in the parameter list. The first connection organelle type is stick. It takes an input which, if valid, allows the organelle to connect to objects and maintain the connection. If it is invalid, the organelle disconnects and no longer sticks to anything. It does not use energy and outputs the direction of the connection if connected and an invalid zero else. The second type is muscle. Here the length of the connection acts as a maximum length. It has one input which sets how long the connection should be. The organelle takes energy when the input is valid. The output is the last valid length input when the organelle is connected and invalid zero otherwise. The third connection type is transfer. It can only connect to other living cells. It has two special parameters, transfer hit points and transfer energy. When a transfer organelle is connected, it transfers hit points, energy, and data to the other cell. The cell making the connection has to have at least one hit point remaining after the transfer to transfer hit points, and 100 energy to transfer energy. The organelle takes one input and transfers the data from that input to the other cell. This will overwrite the output register of the specified slot in the other cell. The organelle uses no energy. The organelle output is the transferred data if connected and invalid zero otherwise. Next, let's talk about evolution in the simulation and how the lifetime of one species is progressing. At the start of the simulation, if it is enabled, members of generated species are spawned with totally randomized DNA and parameters. This adds energy to the simulation, as all alive cells contain energy. New species are generated from successful species by randomly modifying their DNA and other parameters. When mutating a species, a DNA piece addition, deletion, or modification is happening for sure. The red, green, or blue component of the default cell color is modified by 1. Additionally, more DNA mutations can happen, alongside with behavior slot output register default value, surface protein, and mutation chance changes as well. Mutation chance is defined in parts per thousand. When a random species is generating, it is spawned as 5 cells of that species on top of a gas spawner field. If the species is successful and population count reaches 50, it is considered successful enough to mutate. A new mutated species is generated from the original one. Every time there is an egg DNA instruction executed, there is a chance that the new cell will not be the original species, but the mutated one. After few new cells of the mutated species are spawned, and the original species still have a population count over 50, a new mutation is generated from the original species. This goes on until the population count of the original species dwindles, it gets outcompeted. If more than 100,000 cells belonging to the original species were born, or the species is in the GUI list of species, It won't be deleted from the DNA tree of species. In a future release, I want to add visualization of the DNA evolution tree. This will have more impact in that release. One last feature of the simulation I want to detail is overcrowding. If there are too many game objects in one place, the simulation merges them to be more efficient. When non-static rocks merge, their masses get added together, up until they reach a threshold and became static rocks. Gas bubbles, dead cells, and biomaterials all merge with their own kind, adding up energy stored inside them up to 10,000. Living cells take damage due to compression. This can be negated with a strong cell wall with a defense parameter of at least 20. Congratulations, you watched the video. I documented it. 10 years of work. Awesome! I can't stop and won't stop. I have a lot of ideas how to make this simulation even more awesome. Feel free to reach out to me on the Steam forums, on the YouTube comments, or on the subreddit I created. Check out the simulation now in the pinned comment. Subscribe and like the video. Leave a comment. Watch the other videos. See ya!